Okay, Assalamualaikum. Today I will be start with the introduction of our summary of the report. So the first one is, as we know that the sport object tracking is widely being used in sport broadcasting, especially such as soccer, golf, and also rugby. It uses object tracking to improve their coverage. So it is important because it helps to track fast moving object, and also it allow us to analyze their speed, their movement, and also the trajectory. So however, this tracking sport object is not as easy as we thought it is, especially when they move very fast and the lighting of condition and the background also affect how well the system can identify the objects. And also this factor can confuse the system, uh, like when detecting the colors, and also this one will cause like many more wrongly identify something else. So in this project, it involves like creating a real-time motion tracking system, especially for the sports, using the processing software. So it is designed to track the fast-moving objects, and also we can analyze their speed, their trajectory. So this type of technology is actually important in sports broadcasting, which is it can be very challenging. So this one can help a lot more in this field. So we move on to the methodology. So the first one is the physical setup, which is we place the camera on a stable surface to keep the background static. And then this one will prevent the camera from shaking, which is can cause like a lot of more errors in detection. And then we also adjust the lighting. We use the consistent bright, and also the light we use consistent and bright lighting so that it can minimize the shadows behind it, and also it can ensure that the ball's color itself look the same in every frame. That one for get to get the accurate tracking. And the next one will do the object selection, which is we choose a brightly colored ball so that it can create a high contrast against the background itself. So this one will make it easier for the system to identify and follow the object itself. And the last one, we do set up for the calibration, which is we use manual calibration method, which is we just click on the ball on the screen so that it lets the system learn the object specific color for the current environment. So it's not like the green and then it detects like something else green, like area else green. So yeah, it detects the real life green of the color of the ball. So that's all from me.
Okay, so I'm going to be talking about the calculations that are used and why they are used. So first, based on our coding for our system, we use several calculations to track the ball's movement. So firstly, we use the color distance calculation. The system compares each pixel's RGB value with the calibrated ball color using the Euclidean distance formula. As you can see, that is the formula that we used. So if the distance is below a threshold, the pixel is classified as part of the ball. This step allows the system to distinguish the ball from the background. So next, we calculate the centroid, which represents the center position of the detected ball. This is done by averaging the coordinates of all detected pixels. As you can see, that's the formula that we used. So the centroid gives us a stable and precise position of the ball in each frame and is essential for tracking the ball's movement. Okay, so after that, velocity is calculated by measuring the displacement of the centroid between consecutive frames and dividing it by the time difference. This provides an estimation of the ball's speed in real time, which is useful for sports motion analysis. So finally, trajectory mapping is performed by storing all centroid positions and connecting them with lines. This allows us to visualize the path of the ball over time and analyze its motion pattern and direction. Together, these calculations allow the system to detect, track, and analyze the movement of the ball effectively.
Okay, hi, my name is Alia and I will explain what are the technique is used in the making sport object tracking system. So the first technique we use pixel skipping, which is the step scanning. The reason why is it can reduce processing load by 75%. This allows the system to maintain high FPS around 32 to 38 FPS for the fast object detection without lag. Okay, for the next technique, we use color filtering in RGB space to detect the background and the object for the correcting light color. So the reason is we want to get more stable if there is small movement in the background that is not the target object. For the third technique, we use dynamic thresholding so that user can adjust the sensitivity using the up and down key. The reason why is we want to allow the system to adapt to changes in the light on the fly without having to stop the program. Okay, this is our flowchart system that show the data flow from the raw video input to the display of physical information in real time. So our system workflow start with the initialization phase. Here, the program initializes the video object and loads the files in MP4 into the memory to be analyzed frame by frame. So the next step is the calibration process. So the system uses decision logic to detect mouse clicks from the user. So when the user clicks on an object, the system takes the color value of the pixel and set it as the track color. So this allows the system to dynamically adapt to any color of the object it wants to track. So the system will enter the processing phase. So this to ensure smooth real-time performance. So we use the step scanning technique with a value of step equal to 2. So it means the system will only scan every second pixel to reduce the CPU load, thus maintaining a high FPS to track the fast ball movement. At the heart of this flowchart is the filtering logic, which is each scanned pixel will be calculated for its color distance to the target using the Euclidean distance formula. So if the distance is below the threshold, the pixel is confirmed to be part of the object. So its coordinates will be saved for the further calculation. And then for the final phase is involve the calculating a centroid to find the center point of the ball. And then we'll calculate the velocity to measure the velocity of movement. So finally, all of this data x and y coordinate and also the speed will be displayed on the HUD output along with visual neon trail effects.
Now I'm going to explain about our real-time experiment. So this is the video that was produced during our real-time experiment. As can be seen, the ball consists mostly of white color with some red and blue stripe and a very small amount of neon yellow stripe. It is not really visible there, but it is visible on the actual ball. And these choices of ball actually affect a lot of things in our detection. For the analysis of the previous real-time experiment, firstly, the system faced difficulties in correctly determining the ball centroid, which is the center, where in some frame, the ball was detected with an off-center centroid, while in some frame, it was not detected at all. As previously mentioned, some frame did not contain any detection, which is due to the ball multicolor properties. Since our system used a color-based tracking method, this creates confusion for the system to accurately identify the correct targeted pixels. And lastly, due to all of this problem, it caused incorrect trajectory visualization and also velocity calculation, with some trajectory not representing the actual motion of the ball moving. So this might also due to the low resolution and lighting variation from the webcam that were used on our real-time detection. So both real-time webcam and pre-recorded video have different properties that benefit object tracking. For now, the current setup benefit pre-recorded video most as it provides higher camera resolution, better lighting, higher pixel value consistency, lower motion blur, and also a more stable frame rate compared to the real-time webcam. So due to all of this situation, we decided to use a pre-recorded video of an orange ball for our result and analysis, which will be explained later by Aimi. The reason for our choice is that it provides a clearer and higher quality visual input. It also reduces noise caused by the poor lighting and also the low resolution, produce smoother trajectory motion, and also it ensures stable and reliable results throughout the experiment.
So the net is the results of sports object tracking that we use orange ball as a model. The performance analysis for the orange ball demonstrates high computational efficiency by implementing a pixel skipping algorithm, specifically x plus equal to 2 and y plus equal to 2 sampling method. So we reduce the per frame processing counts by 75%. This optimization allowed the system to maintain a consistent frame rate of 32 to 38 frame per second. As a result, the visual lag was negligible, providing the real-time responsiveness that necessary for accurate spot analysis. Next, in terms of accuracy, the system achieved 100% tracking persistence throughout the orange ball's flight path. The Euclidean distance formula was highly effective because the orange color occupies a distinct region in the RGB spectrum, far from the neutral tones of the background. So our calibration phase provided a tight reference point to ensure the centroid remains stable with less than 3 pixels of jitter. So now we move to discussion, trajectory and physics. Okay, as you can see the video here, okay, look for a moment where the neon trail forms a clear U shape at the top. The dots or segment of the line should look closer together at the very top of that U. So this is the visual proof of gravitational decelerations. Okay, this system accurately captured that the ball's parabolic arcs. We observe that the distance between centroid decreased at the peak of the bounce, which correctly reflects the physics of gravitational decelerations. Furthermore, our centroid averaging method proved robust during floor impacts. Even as the ball deformed slightly, the system handled the sudden velocity spike without losing the target lock. The limitation and challenges that we found out while doing this project is lighting variations, where its sudden changes can affect the color consistency. The second one is motion blur, which is it can reduce effectiveness of pixel-based detection at extremely high speeds. And the last one is color overlap, where the backgrounds and the shared similar color with the objects. So it will be potential for false detection. So the conclusion here, the achievement that we got during this project is we successfully implemented a real-time color-based segmentation and centroid tracking. And we developed a dynamic neon trail to visualize complex parabolic motion and impact points. And the last one is we get integrated interactive calibration for color and threshold sensitivity. So while successfully, we identified certain limitations. High-speed movement causes motion blur, which can reduce the precision of color detection. We also noted that the system is sensitive to sudden changes in lighting and background color similarity. So these factors can lead to temporary detection, loss, or false positive if the ball passes in front of an object with a similar RGB value. So that's all from us. Thank you for your attention.